Good morning, Astronomy 1010. Welcome to Lecture 5, Part 1. We are having a sneaky last-minute Zoom lecture because snow forced CCRI to delay or cancel classes, depending on which message you read. Classes were either delayed or canceled before noon, which includes ours. However, rather than meet at noon or completely cancel and then come in for lab, I decided we're all going to watch this video. We're going to do Newton's laws and gravity together on Zoom. And on Wednesday, we will meet in person as scheduled if all things go according to plan. Everyone understand that? We are doing Zoom for Lecture 5, Part 1, and everyone will do the lab today. On Wednesday, the day class will do Lecture 5, Part 2 in person, followed by homework in person, okay? I'll try to have videos recorded so that anyone who misses things can watch it later. Daniel, you can do your lab later when you watch this video, okay? All right. Today's work should lend itself to lecture notes on this board today as well. Last time we learned about motion. Today we are going to begin by studying Newton's 3 laws of motion. So we're going to have several different sets of laws in this class. So far, we've had Kepler's 3 laws of planetary motion. Today, we will focus on, I'm doing this again, on Newton's 3 laws of motion, which were laid out in the Principia Mathematica in the 1600s as not only a refutation of the physics of Aristotle, but also as a guidebook for how we can understand forces and how forces cause things to move and accelerate. These are a classic, okay? The first law is known as the law of inertia. The law of inertia states that an object in motion will stay in motion unless acted upon by an outside force. And we'll underline by an outside force because that's sort of the most important part. They're telling us forces are things with change motion. There's another variation, of course, which says an object at rest will stay an object at rest will stay at rest unless acted upon by an outside force. That's called a corollary. It's a different way of saying the same thing. Why did Newton need to describe the law of inertia? Aristotle had claimed that when you watch a stone roll along the ground, it will eventually come to rest, Aristotle says, by its sort of own volition. It just naturally comes to rest. And his idea about why a stone would come to rest is that Aristotle believed that the center of Earth was the ultimate place of rest in the universe, and that all things desired to end up traveling towards the center of the universe somehow. He believed that gravitas would cause a stone to come to rest because the motion was towards the center of Earth. But Newton could see that that was not quite fair. It wasn't quite fair. Where's my damn meter stick here? Oh, here it is. When a stone rolls along the ground, Newton realized there are frictional forces that act between the ground and the stone, and the frictional forces are actually side to side. That's what causes the stone to kind of eventually slow its motion. the downward motion of gravity is independent of the sideways motion of the stone along the ground. Well, they're slightly related because friction is related to weight, but that's sneaky. In any case, Newton realized that if you were to take this stone and you were to put it into outer space, free of external media, a single impulse or a force or a flick would cause the thing to start to move, and it would never slow down unless other forces acted upon it. In other words, in the law of inertia, Newton had discovered the secret behind the video game Asteroids. And you too know that if you play the video game Asteroids, you can rotate your ship 360 degrees to fire your little pellet gun and break up the asteroids. However, if you apply your thrusters, because the asteroids get too close to the ship, you will begin moving across the screen and you will sort of fly out of control until you rotate your ship 180 and fire some retro rockets to slow yourself down. Isaac Newton did not have asteroids at his local pizza parlor, okay? And he didn't grow up watching Star Wars and 2001 Space Odyssey. He had to figure that stuff out from the get-go before anyone had been into outer space. And that must have been a very difficult thing to come about and understand. Another thing that's cool about this is that Isaac Newton realizes that forces are things which change motion. And if you use motion as a secret code word for velocity, forces change velocities. And last time, what did we define a change in velocity as? How did we define a change in velocity? Who's got notes? Who wants to talk to me and engage with me?
Is it an acceleration?
That's right, Cole. A change in velocity is the definition of an acceleration. This brings us on to law number 2. Law number 2 could be considered the definition of force. It's a legendary math equation. Force equals mass times acceleration. We should take a moment here and we should think about the units of force, because the units are what help you understand a quantity. Imagine I had a 1 kilogram bocce ball and I suspended it in the gravitational field of Earth. Earth's gravity would apply a force, and the force would be its mass times the acceleration that gravity wants to impart to it. But don't we already know what the acceleration of Earth is? Isn't it the same for all objects, whether they be bocce balls or dump trucks or lightning rods or whatever? What's the natural singular acceleration of Earth for all objects?
9.8 meters per second.
Oh, someone's getting fancy with the 2 sig figs. How about 10 meters per second squared? But same thing.
Okay.
But good, 9.81, whatever you like to use. Actually, I think if you get to like, so for everyone on Earth, it's 9.81. After the 3rd or 4th significant figure, the number will change depending on which part of Earth you go to, because slightly different terrain formations like mountains and such, and iron content in the soil can change small variations in little g. People use this actually to as part of GPS in a way. So let's assume that we had a force which was a 1 kilogram mass multiplied by g, which is 10 meters per second squared. Let's see, 1 times 10 would give us 10, and the units would be kilograms times meters divided by seconds squared. Those are our units of force, but, you know, kilogram meters per second squared is kind of a lot to say. So we redefine the units of force in honor of Sir Isaac as 1 Newton. And 1 Newton is defined as 10 kilogram meters per second squared. So those are the MKS units of force. So this is an MKS system units. The third law, I don't know what the title is. It's a legendary statement that says for every action, and action is an old-timey way of saying force, there is an equal but opposite reaction. Reaction could be read as counterforce. The idea behind the third law of motion is that forces always exist as pairs, not in isolation. A rocket engine, for instance, will thrust forward in space only after you send an exhaust pipe of gas pushed out from behind. As you emit a force behind you or thrust some gas out of your rocket tailpipe, the equal but opposite force will push it forward. Another way of sort of examining this law is the somewhat uninteresting case of pressing your finger against a brick wall. Unless you're Superman and have the power to break walls with your finger, if you apply a force with your finger against a brick wall, the brick wall usually doesn't move. And if there is a force, but there is no acceleration, the only logical conclusion is that the brick wall somehow mysteriously presses back against your finger with an equal but opposite reaction. And this also goes for gravitational objects too. When you have a force of gravity between, say, Earth and the moon, it is a single force that exists between two bodies. These three laws can be unpacked in a variety of ways to help you understand how objects move through space. Of particular importance, of course, is F equals ma. That's probably the most important of all three laws. Okay, do you guys have this down? I'd like to erase. Cole needs a second. I need some coffee. Cole, are you all set now? All right. We're going to do another law of Newton. Now we're going to study Newton's law of gravitation. And it's sometimes called the universal law of gravitation because this law of gravity applies to things on Earth as well as things in outer space, even at the galactic or the universe level. Gravitation seems to be a key part of the universe itself. As the legend goes, Isaac Newton was sitting in his childhood home at Woolsthorpe, England, and he wrote in his journal, here's Woolsthorpe Manor, that he was occasioned by the fall of an apple, okay? So he was maybe staring out this window here, and he saw an apple on a tree kind of come loose and drop down to the ground. And he wrote that this was a eureka moment because he realized that the apple could only drop to the ground if it experienced a force. And that force must have been somehow related to the Earth, the gravity of Earth. He then went ahead and made a connection between that force and the force that holds the moon in orbit. He wrote, I realized that the same force pulling the apple to the ground had to pull the moon also down, and that's why it stays in orbit. And so the idea would go something like this. You have a moon, let's draw our moon here. And the moon at the position that I've drawn it on my slideshow currently has some kind of a sideways velocity, right? Actually, let me do this in red. The direction of the velocity is to the right. If Newton's first law of motion is correct, the object in motion should continue in motion unless acted upon by an outside force. And surely there is no sideways force pushing the moon to rest. However, the moon's direction ends up traveling around this circular circle, which would only be possible if there was a second force, a force directing it downwards towards the Earth. In that case, the subsequent motion would be the combination of its sideways velocity and its downward direction of acceleration, and the two combined would push it over to here. But think about what happens next. Next, the moon is here in this configuration. It still has the downward force of gravity applied to it, but because there was no sideways force, it should also still have its velocity sort of pointing tangent to the circle there. So there is no forces acting horizontally. Now horizontal is a little bit skewed, but there's no forces happening in, all right, this is shitty, hold on. Wait, undo. There's no forces happening in kind of this direction, right? So it still has the sideways velocity and the downwards velocity. In other words, the act of being in orbit is the act of falling towards Earth. When we fall towards Earth, we exist in something called a free falling reference frame. Today, we are going to consider the orbit in our lab of the legendary International Space Station. And the International Space Station is a collaboration, a satellite or a space station where people live year-round, and it's a collaboration between NASA, the European Space Agency, the Russians have a module, the Japanese have a module, and people live inside this thing year-round, and they experience what's known as microgravity. It's basically zero gravity. Let's take a look here. In microgravity, we can see people doing all kinds of fun things like somersaults, and they play with orange juice. It must be fun to spend your days working in a low gravity environment. Oh, here's a legendary astronaut. I think he's back on Earth now, but for years he was up, or for a long time, he was up there on the International Space Station. His name is Chris Hadfield, and he would do all these kinds of fun YouTube videos and science experiments about what life is like in a low gravity environment. Some of them are really funny. Let's see, YouTube. Chris Hadfield, I don't know, sandwich in space. He would tell you how to do like ordinary things, like how to make a peanut butter and honey banana sandwich or something in space.
Let's talk about space food.
Chris's kitchen, right?
In the early days of space exploration.
So look at this here. It must be wild to sort of be floating up here in the International Space Station. There are all these little things that you take for granted and forget about. Look at him, there's the honey just floating around, right? And it's really cool. It's actually quite difficult, I guess, to get the peanut butter and the honey out of the jars without gravity, because they kind of just want to splash out and go everywhere. Look, he's got the thing Velcroed. Anyways, there's all kinds of videos. I think he even has one on how to take a poop in space, which is pretty hilarious, okay? You know, how do you do that in a low gravity environment? Now, here's something to think about, students. The International Space Station, right? it's only 400 kilometers above the surface of Earth. You don't suppose that gravity just shuts off after 400 kilometers, right? It looks like they're in zero gravity, but if the moon is 400,000 kilometers from Earth, the moon is still held in place by gravity, right? So if the moon is held in place by gravity at 400,000 kilometers, obviously the ISS would still have the gravity of Earth pulling on it. The reason why they don't seem to experience gravity is because of the thing I was just showing you with Sir Isaac Newton. They are in a state of free fall where they're basically falling towards the Earth due to gravity, but their sideways velocity carries them in this direction, and they basically miss the Earth. They constantly fall to Earth, but their sideways velocity pushes them out of the way. Now, I'm not sure exactly how he went from here to understanding that mass was one of the components, but I also wouldn't have time to teach it to you even if I did. What we want to do is we want to learn how to understand his law of gravitation, the one that he came up with, and we want to do so from a perspective the way Isaac Newton imagined it. So my eventual goal is to help you to understand this formula here, but I'm going to start with a weird version which does not include big G, the universal gravitational constant. Bear with me here for a sec. The way Newton laid it out in the Principia Mathematica is that there are two masses, one which is called M1, the other which is called M2. And they are separated by a center to center distance. This is important. We always measure the distance from center to center. The distance will be called little d. Newton's version went like this. Force is proportional to the product of the masses M1, M2, and inversely proportional to the square of the distance. And I want to write down those words next to it. Directly proportional to the product of the masses and proportional to the square of the distance. Or I've used a new symbol, one that you're not too familiar with. The Jesus fish thing means proportional to. Proportional to also means it varies as. A proportional symbol is a powerful mathematical operator that can let a scientist quickly evaluate how a quantity like force depends upon the properties of things going into the equation. Okay. How does this work? When you plug in numbers using a proportionality symbol, you do not get a direct result, a magnitude with a number in newtons. You instead find out how many times the force will vary. So for instance, the way we would use a symbol like this is we would say, if I double both masses. So for instance, if you were to simultaneously double the mass of Earth and double the mass of the sun, the force would be directly proportional to the product of the masses. And therefore, the force would vary by a factor of 4 times stronger. Notice that when I double both masses, I only have to write the part of the equation that's m1 times m2 because I didn't change the distance. So this could be considered example number 1. In example number 2, if I double the distance, between the objects, then the force is inversely proportional to 1 over d squared. And the new force would be 1/4 is great, or 4 times weaker. Do you guys want to give it a shot? I'm going to try to erase this, okay? Can I erase this, Cole? All right. Okay, let's try a third example. If I have the distance, what would happen to the force? What is force proportional to here? Let's write it symbolically with variables first. Okay, I want someone to answer me. Force is proportional to which symbols do I conclude if I'm having the distance?
The distance.
Right, but how do I write it in symbolic form here? Like, do I write force is proportional to distance like that? Is that what I do?
No. Half.
No,
So
I
1
don't
over
want you-
2.
I don't want you to put the numbers in. You're misunderstanding me. I want it in terms of variables. For instance, let me write the whole thing in terms of variables. The whole thing would be m1 times m2 over d squared, but I don't need to include all this because I'm not changing all of those quantities. Do you understand what
Okay.
I'm saying?
Yeah. So you only need d squared.
Like this? Is that how I write it?
No.
No, that's not how I write it. So you're not being clear enough with me. How do I do this?
Would it be m1 times m2 divided by d?
Unfortunately, it wouldn't because we're not changing the masses. In general, it is that. But in this specific case, you don't use the masses because we're not changing the masses. They stay a factor of 1. They do not affect things.
Is it 1 over d squared?
That's what I want. Since we're only changing the distance, we only put in the equation, leaving the distance in there. It's 1 over d squared. Okay. Now this is proportional to, what would we sub in next? Now we have to factor in the half, right?
Are you gonna instantly flip the half, or are you just gonna put in the half?
I'm going to write in the 1/2 squared like so. I'm going to substitute it in for d in parentheses. Now I will distribute the square. I'm going to change it to an equals because I can now evaluate this. Before it was proportional, but now we're going to evaluate. 1 over 1/2 is 1/4, and now you flip it. It's 4 times stronger. The new force is 4 times stronger than the old force. Notice that when I change the distance, I only include the distance, not the masses, and vice versa. That's how proportionality symbols are used. Now, the reason why Newton wrote it in terms of a proportionality symbol is because we actually need to measure the strength of gravity if we want to figure out what the actual force is. Can I erase this? Okay. The problem with writing an equation like this is that in the MKS system of units, masses must be measured in kilograms, distances must be measured in meters, and forces must be measured in newtons, which we just learned are kilogram meters per second squared. Oh, sorry. Kilogram meters per second squared. Human beings invented the kilogram. They also invented the meter, and they also invented the second, and therefore they also invented the newton. For instance, Nazier might have a conception of space, but it was our idea that this should be a fundamental unit of length in space. But human beings did not invent gravity. It is up to nature to decide how strong she wishes to tug. For instance, if I have two objects, each which have a mass of 1 gram or something, how strong will nature tug on them if I hold them 20 centimeters apart? I have to ask nature that question. And that turns out to be hard because gravity is a very weak force. In fact, gravity is so wimpy that you really only start to notice gravity exists when you build up an entire planet's worth of matter in one space. Even asteroids can sometimes have very weak gravity, which barely binds you to the surface. The person who actually figured out how to measure gravity was not Isaac Newton, but a scientist who came years after him named Henry Cavendish. And in the legendary Cavendish experiment, Henry Cavendish figured out that he could actually measure a small deflection of gravity, kind of an ingenious device here. Let me show you a slightly modern version of his original idea. This is a pretty cool illustration of it. Okay, so what he did is he invented something called the torsional pendulum. I don't know if he invented it, but he certainly used it. A torsional pendulum has a very thin fiber of wire, and attached to it is a thin rod on which he attached 2 lead spheres. And I think he used lead because they were high density and therefore high mass. Since they were suspended from a torsional fiber, they could kind of rotate horizontally, but the gravity would not be able to pull them down. So they were sort of weightless in the horizontal direction. Sorry. Now, the second thing he did is he took another rotating arm and he attached 2 larger spheres to it, and he sort of made them be able to pivot. And he put a small mirror attached to the fiber. And in the modern version of the experiment, you actually shine a very thin laser, which can bounce off the mirror and be measured. The deflection of it can be measured on a scale. If gravity can pull the 2 spheres together, if you can get a small deflection of gravity, gravity will pull these 2 spheres. It will cause the fiber to twist. And then any deflection in angle, even if it's tiny, can be measured on the wall. And here he's exploiting the fact that a very tiny deflection in angle will produce a big displacement in distance if the laser or the light is shined at a far enough distance. I don't know if that makes sense to you guys, but here's my cat laser that I just bought to terrorize my cat with, right? And you can make the tiniest little deflection in angle, but if the laser, if the laser is close to the wall, small changes in angle only lead to small displacements. But because of the small angle formula, which you studied in chapter 2, a very tiny change in angle will lead to a bigger and bigger shift in measurement on the wall. So you can measure even very tiny deflections. Very ingenious idea. Legendarily, Cavendish did actually measure a small deflection, and he was able to use this to compute what is now known as big G. Big G actually turns the law of gravity into an equal symbol. And big G is known as the universal gravitational constant. And it was first measured by Henry Cavendish and something. Okay. So anyways, it has the same value for all time it's 7 times 10 to the negative 11 meters cubed per kilogram per second squared. So the units are a little bit insane. If you have to think of big G as something, you should think of it as an index of the strength of gravity. That's how I think of it. In other words, it tells us how strong gravity tugs on objects. And by the way, gravity is a weak ass force, because if you have two 1 kilogram masses, which are about the mass of a brick, separated by 1 meter, which is about the length of this board, they will be tugged on by 7 times 10 to the negative 11 newtons of force. That is a weak ass force for 2 bricks to experience. You wouldn't even be able to notice that if you were holding them in your hands. This is the final version of the law of gravitation, thanks to Henry Cavendish. I will make an interesting historical note. You would think that Cavendish would be excited to publish Big G, as in like, yo, dog, I'm the first scientist that ever figured out how strong gravity is. And gravity is a fundamental force. So I'm like now deeply in touch with the universe, right? You know what he published his paper as? Yeah, cool idea, right? He actually published the paper as on a new method of estimating the mass of Earth. He thought what would be interesting to people was to use Big G to calculate Earth's mass to a high degree of precision, which of course is not uninteresting, right? But I think that understanding how strong gravity is like beyond Earth. It's like the whole universe's fundamental force. And for some reason, I don't know, it's funny how even what a scientist does at some period in time, it's not how we might think about it later on, right? He thought that the most important thing to humans would be the mass of Earth. Nowadays, we think, whoa, if you discover a fundamental force, that makes you a lot more badass, right? So interesting how history kind of changed the way we look at things. Anyways, why don't we try a simple calculation together? We all know, of course, that there's a force of gravity between Earth and the moon, right? Let's calculate it. I'm going to erase this stuff. So, example. Find the force of gravity between Earth and the moon. To do this, we will need Henry Cavendish's result for the mass of Earth, 6 times 10 to the 24 kilograms. By the way, do you see that symbol there? The circle with the cross in it? You're going to see me use this a lot. This is the universal symbol for Earth. Then the mass of the moon, 7 times 10 to the 22 kilograms. I guess you'd have to go and do Henry Cavendish's experiment on the moon to figure that out. The distance between them to 3 sig figs is 384,000 kilometers. Our goal is to compute the force. First, we need MKS units. Convert D to meters. That's our first job. Mia.
Yes.
I recommend you for this task.
All right.
Please use the 4 steps of dimensional analysis for me.
All right, and we're figuring out the meters. All right, so first we write down the distance.
Yep.
384,000.
Like that?
Yeah, exactly like that.
You've already done something wrong.
Oh.
Why don't you read the actual line that I wrote for the 4 steps of dimensional analysis? This is why we have to go through this, Mia, because you guys don't pay attention to the details that I pay attention to. What is it?
trying to find that in my notes.
It would be like the second day of class or something.
Uh,
I-
yeah, I'm not sure.
Well, look, I could probably find it before you can find it. So
Says write down the number to convert with
Units.
yeah,
We
yeah.
have to put down the, you have to put down the distance in kilometers.
But you have to actually put down the kilometers, right?
Yeah, that's what I'm saying.
Yeah.
Yeah,
Because Mia,
uh,
if you don't write down the units, it kind of misses the whole point of dimensional analysis, right? Which is to
yeah,
look
yeah.
unit. Okay. Anyways, you might think that's a small detail. I don't, but
Oh, no, it's not. It's not. I
Okay.
just overlooked it. But yeah, at that point,
no,
what we're gonna, so after that, we're going to times, and something wrong with that marker.
times what?
Oh, so on
I was trying
top,
to
we're gonna put,
wait, you times a division bar.
yes.
Okay.
So on top, we're going to put the, I think we're supposed to put the unit that we're going to be converting to. So 1 kilometer
No,
is,
whoa.
no, I'm saying 1 kilometer would be on the bottom.
Look, you don't touch any fucking numbers until your units are in place.
Okay,
There's no one, there is no none. It's just units. That's the idea.
okay, sorry.
In other words, I need you to give me a unit on top and I need you to give me a unit on bottom. That's why we do this.
Yeah, so on top, we're going to put meters because that's what we're converting into.
Correct.
And on the bottom, we're doing kilometers.
Right. Don't put any ones in. All right. Don't get
Okay.
happy slappy with the ones. Now you can get happy slappy with the ones. Step 4 is to use the conversion factor to put the numbers in.
Yeah. So, all right.
What's your conversion from meters to kilometers? You can look in the notes,
That's going to be times 1,000.
but where does the 1,000 go?
1,000 is on top.
Fine. What goes in the bottom?
Just 1.
That's right. The numbers go in at the end, so you don't make
Yeah.
a mistake.
Mhm.
All right. Can you do this in your head?
Uh,
Zeros.
I'm 3 in both. So
So
I'm pretty sure we just add the zeros from 1,000.
how about 384
Oh, scientific notation.
because it's bigger than a million, right?
Yeah, it'll be 10 to the 6, I believe.
That's right.
That's how many zeros?
384 million.
Yes.
You can just write
Yeah.
it like that. We'll leave the 384 and then we'll pack the zeros into 10 to the 6. Okay. Second, this is what we call in physics plug and chug. Okay. Plug and chug is when you plug the numbers and the units into the equation. Okay. So the force of
Right.
gravity is big G. Now, because this is your first time, I'm going to do the units in blue. Big G is 7 times 10 to the minus 11 meters cubed per kilogram per second squared. We're going to multiply that by the mass of Earth, 6 times 10 to the 24 kilograms. We're going to multiply that by the mass of the moon, 7 times 10 to the 22 kilograms. And I want you to watch how I write this on the bottom. Open parentheses, 384 million meters squared. Now, y'all might be thinking, oh, I get it. I get it. The parentheses are for the calculator, right? Wrong. The parentheses are not for the calculator. The parentheses are there for your unit balancing purposes. The square is distributed to both number and to unit. If I had not put the parentheses there, someone might think I mean 384 million square meters, which is not the same thing as 384 meters squared, right? 384 square meters is an area, but 384 million meters squared is a distance that is squared. Ultimately, it's also an area. Okay, but it's not the same number. All right, we ready to plug and chug? Now listen, from now on, we're going to be doing this in class. I'm going to walk around, and if you can't do this, I'm going to ridicule you in front of the general populace. So you better figure this out with me, okay? We'll start with big G. 7 exp negative key 11 times 6 exp 24 times 7 exp 22. Watch this, no parentheses. Divide by 384 exp6. Now I'm going to hit the square key because I got to square it. But doink, that squares it. And then I finish the job by hitting equals. Okay, I don't know why there's a negative sign there. I screwed something up. But that's the right number. Let me try that again. 7 exp negative 11 times 6 exp 24 times 7 exp 22 divided by 384 exp6 squared equals. Is that what you guys got? Hold up your calculators. Yes, yes. What should I round this number to?
2.
Uh,
Well, what about that?
2 times 10 to the 20th.
Yeah, you don't want to call this 2 because there's a times 10 to the
Just
20.
rounding the main number to 2.
You could understand how that might be confusing for other people to hear though, right, Ethan?
Yes.
2 times 10 to the 20 what?
Newtons.
That's what it's going to be, but let's see why. Meters cubed will cancel with 3 meters to give you meters to the 1. Kilograms cancel with 1 kilograms. And that means at the top you have a single kilogram times a single meter over a second squared, because the bottom of the top is the bottom. And kilogram meters per second squared is a Newton. So that's 2 times 10 to the 20 newtons of force. Let's see how we're doing on time here. 12:30. What do you suppose is stronger? The force of gravity between Earth and Moon, or the force of gravity between Earth and the Sun? Take a guess.
Earth and Moon.
Okay. Cole says Earth and Moon. Let's find out if Cole is right. Cole, in theory, we could calculate it to be sure, right?
I was just taking a shot in the dark. I really don't know.
Oh yeah, that's what I wanted you to do. I wanted you to just shoot from the hip. No reason to know the answer to start, okay? Does everyone have this down? We're going to try another sample problem to see if you all can handle it. Don't forget that answer. Okay. This is example number 2. Let's find the force of gravity between Earth and the Sun. So this is example number 2. Still got the same mass for Earth. The symbol for the sun is a circle with a dot in it. That's actually from Egyptian hieroglyphics. That's where we get that. An M circle dot means M sun. The mass of the sun is 2 times 10 to the 30 kilograms. Maybe I'll tell you how we get that sometime. The distance, of course, is 1 AU. And you've learned that 1 AU is 150 million kilometers. Same issue. The first step is to convert the distance to meters. So we start with 150 million, wait for it, Mia, kilometers. We then multiply by a division bar. We put kilometers on bottom. We put meters on top. We cancel out. 1 kilometer is 1,000 meters. Hey, Mia, are you better now? How would I put that into scientific notation? No calculators.
Well, it starts out as 10 to the 6, so that's 3 more zeros. So that's going to be 10 to the 9th.
Very good.
Is that right? Yeah.
Yep, 150 billion meters. Exactly correct. Okay, second step is plug and chug, just like before. The force between the sun and Earth is 7 times 10 to the negative 11 meters cubed per kilogram per second squared times, let's say, the mass of the sun, doesn't matter which is first, 2 times 10 to the 30 kilograms, times the mass of Earth, 6 times 10 to the 24 kilograms, divided by 150 billion meters squared. Okay, plug and chug, students. You saw me do it before. You do it this time. You guys all got it right, the people I'm talking to. Tell me what you get. What'd you get?
4 times 10 to the 22nd newtons.
That's right. Let's see how they got that, okay? So it was 7 exp negative 11 times 2 exp 30 times 6 exp 24 divided by 150 exp 9, square it, and then equals. How should I round that to 1 sig fig?
That's just going to be 4 times 10 to the 22nd power.
Cole, what did we learn? And the units are newtons, right?
Yeah.
This is sun and earth. And this here is the moon and earth. What's stronger, Cole? The force of gravity between the sun and earth, or the force of gravity between the moon and earth?
The sun and earth.
Yeah, we learned something new. Now, you can do penance for me, Cole. Here's what I would like you to do. I would like you to compare the forces. And in our class, compare means take the ratio. And I want you to try to do this, Cole, without a calculator. We're going to divide the force of gravity between the sun and earth by the force of gravity between the moon and earth. So in the top, we will have 4 times 10 to the 22 newtons over 2 times 10 to the 20 newtons. Have you ever divided numbers in scientific notation in your head before?
I'm pretty sure you just subtract it, right? It would just be 2 times 10 to the second.
You divide the lead digit, but you subtract the powers. That we have to be clear about that, okay? 4 divided by 2 is 2. But yes, 22 minus 20 is 2. And Cole, what are the units of the 2 times 10 to the 2?
Newtons.
No. Newtons on top cancel with newtons on bottom. There are no units to this number. What is this number in plain English? What is 2 times 10 to the 2?
Ratio? A percentage?
As a
Neil?
number, it's 200.
Yeah, it's a 2 followed by 2 zeros.
Mhm.
And it's not a percentage. Well, you could think of it as a percentage, but that's kind of weird. It's a factor. It's 200 times greater. That's what it means, right? Like, for instance, coal. If you have 10 cookies, right? And I have 5 cookies, and we compare cookies, 10 divided by 5 is 2. But that doesn't mean 2 cookies. That means you have 2 times more cookies than me, right? So this divided by that means 200 times stronger. So in other words, Cole, the gravity of the sun is 200 times stronger than the gravity of the moon, right? That's what that means. Cole, we live in the ocean state. All of our friends and family members, the fishermen, the caw hoggers out there, the people catching crabs down at Narragansett Beach, whatever. They know about tides because we live in the ocean state. And what is the cause of tides on Earth?
The moon.
Can I answer?
Moon.
Oh, never mind.
Go ahead, Daniel. You want to ask a question?
No, I was just saying the moon as well as coal.
As well
As
as
your-
what?
Along with coal, I also said the moon as an answer to your question.
Gotcha. Okay, I understand. So guys, here's my question back to you. How is it that the moon causes tides when the sun's gravity is 200 times stronger? Why doesn't the sun cause tides?
It's the moon and sun that cause
Be-
tides.
Probably because the sun is further away from.
Okay, let me take each of those answers in question. It is true that the moon and the sun cause tides. I'm going to tell you about that in just a second. But doesn't it seem weird that the moon is the more primary cause of tides? Now, the second contribution was Lionel, I believe. Lionel said, well, the distance to the sun is farther. It is true that the distance is farther, but didn't we account for distance when we computed gravity? Even though we
That
put
is
in the
true.
farther distance, we still got a bigger number because the moon is, I'm sorry, because the sun is a 2 followed by 30 zeros, and that overcompensates for the distance.
It's the
Say that again?
no, I'm just going back to myself.
That's okay. Listen, whoever said, if that was Preston or I'm not sure who, the sun does contribute to tides, but it is not the primary cause of tides. Okay, Ethan, we'll see you in a sec. The primary cause of tides is the moon. And that's because the tidal force is caused by gravity, but it's not the same as gravity. Let's do some notes on that.
Question before you do the notes. I'm just curious. Is there an actual symbol for the moon? I see that you already did this. The
Very
symbol for the
interesting
Earth.
question.
Yeah.
The symbol for the mass of the moon, there is one, and it's like a little crescent moon. But I find it really hard to draw little crescent moons, so sometimes I just use an M. But to be honest, it's a little crescent moon is the astrological symbol for moon. I believe so anyways. Nice question. Okay, by the way, there are symbols for all the planets. After that, you know those stupid astrology symbols they use? Oh, actually, the symbols aren't stupid. Astrology is stupid. The symbols actually predate astrology, depending on whether you think of Ptolemaic Western astrology or whatever. But the symbols are, they're Grecian symbols. All right. Let's learn about something called the tidal force. A set of notes to help you understand that tides are slightly different from gravity. So here are some bullet points. Indeed, tides are caused by gravity. But there's another point. The so-called tidal force is not the same as the gravitational force. It's related, it's caused by gravity, but they're slightly different. The tidal force, the force that causes tides, is a differential force. Underline that because that's the key word. A differential force is a delta force. And I ain't talking that Chuck Norris delta force. I'm talking that change in force from the front to the back of an object, okay? It's a tidal force, it's a differential force caused by gravity acting over an extended object from, say, front to back.
I got a question.
Yeah, sure.
Will you relate this to like when a car is transferring weight from the front to the back, like like a front wheel drive car type of thing? Like weight transfer in a car?
I wouldn't do that. That's a confusing analogy because first of all, you're talking about weight, which is a gravitational force downwards.
Okay.
And it's still not a differential force because when you have front wheel versus back wheel drive, the forces involved are just on the front. The front tires are pulling the force, or the back tires are pushing the force, right?
Okay.
But in tides, you have gravity acting simultaneously across all parts of the body. For instance, here's another note. The tidal force is what we would call a gradient of force. And a simplified version of the gradient is the change in force is the force of gravity acting on the front minus the force acting on the back. But it's not just as simple as it acts front and back. It actually is acting on all parts of the object at different intensities. In fact, in the language of calculus, or in the language of proportionality arguments, which we just learned about, the tidal force is different than the gravitational force because it is proportional to 1 over the distance cubed, not 1 over the distance squared. And if you remember the difference between 1 over d squared and 1 over d cubed, they have a different kind of dependency. I don't know if you guys remember your algebra class, but if you had to graph these two equations of y versus x, if you did 1 over d squared, let's see if I can get this here. 1 over d squared looks like this. I guess this would be force versus distance, not x versus y. But 1 over d cubed looks like this. Which means when you're far away from the object, gravity is more intense than the tidal force. But when you get closer and closer to the object, because for tiny numbers, d cubed will be, okay, the denominator of d cubed will be smaller, so the whole fraction will be bigger. If you're less than 1, 1 over d cubed actually gets bigger than 1 over d squared. And that means close to an object, tidal forces are greater in intensity than gravity. Let me explain this using cartoon numbers, okay? Do you guys have all those notes? Because you want that. I want to do cartoon numbers and I want to do percentages. Let me draw the Earth and let me remind you that the radius of Earth is 6,400 kilometers. What would that make the diameter of Earth?
That would be 12,800 kilometers.
Good. We just learned that the distance to the moon is 384,000 kilometers. what percentage of the distance to the moon would the diameter comprise? As a percentage of distance, 12,800 kilometers compared to 384,000 kilometers. First, give it to me as a decimal. Punch that into your calculator. What'd you get?
0.03,
Which is what is a percentage?
3%.
That's right. And that means the front side of Earth is 3% closer to the moon than the back side of Earth. Let's imagine that we could take a planetary-sized cheese grater and slice the Earth into hyperfine slices of gabagool, okay? Like we were down at the deli on Federal Hill, okay? Some
Gabagool.
yeah, exactly. Hey, all right. So gabagool or maybe provolone, okay?
Yeah,
Now,
yeah.
I'm gonna, for the vegetarians among us, now I'm gonna slice some provolone Earth, a slice so incredibly thin at the front that this planetary gabagool, this planetary cheese, has such a small amount of mass that if I were to calculate the force of gravity between the moon and just that little slice, the force of gravity would be, I don't know, 40 newtons, just for kicks and giggles. Imagine I could slice an equally thin gabagool on the backside of Earth. This slice would have the exact same mass because it's exactly as thin as the first slice. But the slice at the back is 3% farther away from the moon. If the force of gravity is proportional to 1/d squared, that sort of implies that 3% change in distance should be a what percent change in force?
A decrease.
No, because it's 1/3%, right?
Increase in force?
If you, sorry, this should be a decrease in force. Yes.
Yes.
A decrease by what factor? Well, it should be increasing by 1.03. That's the factor by which you're increasing the distance, but it's squared. Oh, wow. I thought I was going to get something different from that. So it should be a 6% change in force. I don't fucking know. I'll tell you what. Why don't we just make up a number? The force will be less. Do we all agree on that? Okay.
Yes.
The force will be less by like, I don't know, maybe it will be 30 newtons now, something like that. Okay. So that means if you're the Earth, there is a gradient of force. The moon is, so just like the Earth tugs on the moon also tugs on Earth. It's a single force according to Newton's third law. But the moon is tugging on the front of Earth stronger than the back of Earth because the front side of Earth is 3% closer. And that means that there is a tidal force or a differential force of 40 newtons minus 30 newtons, or a 10 Newton differential that's acting across the body of Earth. And if you're Earth, this differential force is a shear force, a side-to-side force that's pulling you apart. If you look at a picture of how the tidal force works, that differential force will manifest itself as a kind of stretching of the Earth. From the Earth's reference frame, the differential force acts, let's go down here, as a side-to-side force pulling the Earth apart. And this is why we end up having 2 high tides per day. You get a high tide in the direction of the moon, but you also get a high tide opposite the moon because it's being stretched apart. Conversely, if that's troubling to think about, imagine instead that the middle of Earth is also slightly farther from the backside of Earth. So you get a pulling hardest here at the front, and you get the middle of Earth being pulled away from the backside. Not only does the ocean bulge in the direction of the moon, the atmosphere around Earth will also bulge in the direction of the moon, and even the rock underneath your feet will bulge in the direction of the moon. The rock under your feet deforms by roughly 3 centimeters each day in the direction of the moon. And this warps the Earth from a spherical shape into a slightly elliptical shape known as an oblate spheroid. An oblate spheroid is an egghead way of saying a football, okay? I hear that's a popular thing this week. Now, fine, there's a differential force, there's gravity. A pesky student might say, well, Brendan, didn't you say the moon's gravity was 400 times greater? Why shouldn't this be happening for the moon? And I would say to you, well, it does. I mean, sorry, why shouldn't this be happening for the sun, right? It should happen for the sun, but the issue is that the percentage of Earth's diameter is not the same for the sun. For instance, if this is Earth and it's 12,800 kilometers, the sun has a distance of 1 AU, or 150 million kilometers away. So the diameter of Earth as a percentage of the distance is 12,800. Why don't you guys divide this up by 150 million, and what do you get? Since you won't answer that question, I guess I'll have to do it myself. Yeah. How do I interpret that number? Good job. I round it to 9 times 10 to the negative 5, which means 4 zeros and the 9 goes in the 5th place. 0.12349. What is that as a percentage? Who knows how to do percents?
Is that 9 1,000ths of a percent?
Very good, or 9,000ths of a percent. But we would write it as 0.009%. Yes, but Cole, exactly. 9,000ths of 1%. You could say 9 1,000ths, I suppose. That means the front to back tug is a smaller percentage change, right? So in other words, if the front side of Earth, let's say the front side of Earth gets tugged on by 400 newtons, it's clearly hundreds of times stronger than the moon. But by the time you get to the backside, that tug would only be like 399 newtons. So at every point on Earth, the force of the gravity from the sun is stronger. But if you look at the differential force, it's now only 400 minus 399, or 1 Newton differential. And that means it's possible to say two things that sound contradictory, but are not. The sun tugs at all points on the Earth 200 times stronger than the moon tugs on Earth. But the tidal force, or the differential force of the moon, is still stronger than the sun's because it's a subtraction front to back, and the percentage change is a greater fraction of the Earth-Moon distance. In other words, the sun will affect tides, but by a smaller fraction. And in fact, that changes depending on your phase of the moon. Think about how the moon rotates around Earth, right? When the moon is at either full or new phase, it's in line with the sun. And during this time of the month, fishermen know about this. These are especially strong tides called spring tides. And in fact, I think the one with the new moon is called a king tide. For some reason, if you're on this side of Earth, I think the king tide is a bit stronger than if it's on the full moon side. But in general, these two tides are called spring tides. Conversely, during first quarter or third quarter moon, the moon is in a perpendicular direction to the sun. So the moon's tidal force gets slightly offset by the sun's, and you get slightly weaker tides. If you actually plot the phase of tides in the moon, if you plot the tidal variation in Narragansett Bay over the course of a 1-month period, it kind of looks like a sinusoidal function with high and low tides. But leading up to spring tides, it gets a bit higher. And then down to neap tides, it gets a bit lower. It's a bit complicated to check out that graph. Let's write that down. This means we have two different tides. We have spring tides twice a month are at full or new moon. And these are extra strong tides. And then we have neap tides at first or third quarter. And these are extra wimpy tides. Learning a little bit about tidal variations. How am I doing on time? Okay. So, that's a perfect lecture. We learned about Newton's 3 laws of motion, law of gravity, and we learned about tides. That was 3 big modules I'm satisfied with. Now, we're going to be doing a lab today on something called Newton's version of Kepler's third law. I'm going to teach you about that. That's going to be a formula that we study in person on Wednesday. Capiche? The nice thing about this week, weirdly, being, I'm going to repeat this again, even though I've said it to you guys already once. One nice thing about us doing this last lecture on Zoom is that normally section 001 would have to try to do lab and homework on the same day. And then on Wednesday, section 002 will have to try to do lab and homework on the same day. And yes, that's going to suck, but I can't think of a better way to do it. And if you think carefully, you'll realize there probably isn't a better way. However, this week, we'll be able to all do lab together today. I know, does anyone have to go to class or something? Someone said they had to bounce. Daniel, you have to go to work. No big deal. Either
Yep.
secretly watch this at work or watch it later, because I'll post it after the class, okay? But on Wednesday, we'll all have lecture and then we'll all do the homework together. The one thing about that is I've got to figure out what room to do it in. I don't know, I'll have to count heads, but 13 times 2 is 26, and I think 26 might not fit in the lab room. So we can either try to do it all together in the classroom or we'll just hijack another room that's empty. Does that sound like a plan? Okay. Do you guys want a quick 10-minute pause for tea before we start the lab? Does that make sense to everyone?
Okay.
All right.
Yeah.
So it's 1 o'clock iPhone time at 1:10 or 1:50. What do you want? You want 10 minutes? You want 15 minutes? I don't care. What's best? 10, says Cole. Get it over with, right? Fine. 10 minutes. I'll see you in 10.
Professor, can you aim a little bit?
Yes, I absolutely can. And I'll put it on speaker view here. So that way you can get the rest of that, right?
Yeah, thank you.
Okay. All right. I'll see you in 10.
All right.
Okay, Astronomy 1010, welcome to Lab 5, calculating the period of the International Space Station. To answer Cole's question, this is a lab where we don't really need to print out any ditto because I kind of made this lab up. I've changed all of these labs a little bit, but this one is entirely my idea. And my thinking, Cole, is this. This chapter represents a real kick in the pants in terms of math and calculator operations. And one of the big formulas that we're going to learn this week is a modification to Kepler's third law of planetary motion. And I'm going to have to cover this in lecture next time. But Isaac Newton basically modified Kepler's law of planetary motion so that he could account for how gravity changes the period of planets when you're not orbiting the sun. In other words, originally in Kepler's law, we had p squared is equal to a cubed. And in Kepler's version, the period was measured in years and the distance was measured in AU. But in Kepler's version, the equation only works for planets which orbit the sun. It doesn't work, for instance, for the moons of Jupiter, which are orbits that are not around the sun. Newton realized that p squared equals a cubed could be made to work for any two objects if he included the effects of gravity, and that adds this term. Because I've experienced that this formula causes a lot of difficulty in calculation, it seemed worthwhile to have a whole lab on it where we practice punching it into the calculators, and that will also give us some good training for our exam. It'll also let me cut down on the homework that we do this week a little bit. Okay, so what we're going to do is we're going to do a lab where we basically calculate the period of the International Space Station. And you'll remember that in today's lecture, I told you that the I.S.S. Is an orbiting space station which goes around Earth. The altitude, the height above Earth, is about 400 kilometers. And if you know when to look, you can actually see the I.S.S. pass overhead. At night, you'll see a very bright star. It's even brighter than planets. It's a very bright object, but it's clearly not an airplane because it's in space, and it travels very quickly across the sky. It's kind of a fun thing to see. So I thought we would start by just sort of calculating the period and practice that equation. To do so, all we're going to need is a nice piece of paper. I'm going to use some sort of fancy graph paper here. And we want something to make a circle with. And that thing could either be like a little circle maker. I'm actually going to use a right proper compass. You might even use the lid of a coffee cup or just the lid of any cup. You also could use, for instance, a roll of tape, whatever. Find something circular. Okay, sure. We can work with that, Mia. Sorry, I was petting my cat and I've got cat hair on my nose. It's driving me crazy. Okay. Yeah, we might want it to be a little bigger than a coin, Ethan, because we want the diameter to be, oh, the other thing that would be great to have is a ruler. I'd like the diameter to be like 2 to 3 centimeters, if you can do that. Let's see if I can connect to my phone, and I'll show you how this is going to work. Here's a nice piece of graph paper. I want to make use of this. It's got a little thing on it. I don't know why it says 15 people, but. And so let's do this. Let's start with our name. Okay. You guys can see that. We'll do AS1010. And if you're in the Monday lab, put 001. If you're in the Wednesday lab, put 002. I'll be doing this again with the night class tonight. And then this is lab number 5. And we can just call it the period of the I.S.S. Okay. Please label it lab number 5. That really helps. Okay, so what I'm going to do is I'm going to set my compass to a radius of about, I don't know, 2 centimeters, maybe 2.5 centimeters. Okay. Doesn't matter too much. And I'm going to sort of find the center here, and I'm going to draw a nice, oh, medium to big sized circle. Sorry, something fell behind me, and I'm worried that it might have broke. Oh, shoot. Put a dot at the center, and let's not only draw on the radius, but let's draw a little height above it for the International Space Station. I'm going to represent the ISS as kind of a box, okay? Some solar panels on it. We're going to have some givens here, okay? So we know the radius of Earth is 6,400 kilometers. We know that the mass of Earth is 6 times 10 to the 24 kilograms. If you look up on the Wikipedia, the mass of the I.S.S. is 400,000 kilograms. They call it 400 metric tons, and a metric ton is 1,000 kilograms. The height of the I.S.S. is roughly 400 kilometers above the surface of Earth. Now, so our goal today, is to calculate the period of the I.S.S. using something called Newton's version of Kepler's third law. And Newton's version of Kepler's third law, oops, sorry, I got some focus issues here, goes like this. P squared is equal to 4 times pi squared times a cubed divided by big G times open parentheses. It's the sum of the masses. So in our case, it's the mass of Earth plus the mass of the I.S.S. Sorry. Guys, will you copy that down? I've got to get these cat hairs off my nose. I'm going crazy. All right. Do you guys have that down? Ethan, Cole, Mia, Ethan? Okay. So here's what I want us to do. I want us to focus on getting, oh, by the way, all of this formula requires MKS units, which means P, the period, will be in seconds. A is the center to center distance. I want you guys to watch this trick. Here, the distance between the objects is an h, but the distance A, label this, is the center to center distance from satellite to the center of Earth. A must be in meters, and the total mass, hold on a second, I've got some, can you close that door? The dryer is going nuts. Just hold on a second. I don't know if that's coming up in the recording, but the washing machine is imbalanced, so it's really making a lot of noise. The total mass should be in kilograms, MKS units. Okay, first we're going to focus on the A, which is the center to center distance, okay? So let me see if I can just kind of zoom out a bit. Oh, no, I guess not. manual zoom. A is h plus the radius of Earth, which is 400 kilometers plus 6,400 kilometers. So A is 6,800 kilometers. We've got to convert that to meters. Ethan Brown, would you be kind to help us out with that?
I'm not gonna lie, my computer's lagging a little bit, and I haven't even written that down yet. Give me 1 second.
Why don't you take your time to write it down and then we'll guide you through it, okay?
All right.
I hope that's not on my end. I hope that's your end.
No, it's definitely my end. My Wi-Fi has been terrible today.
Okay. I hope you guys also agreed with my decision to make this on Zoom. I don't think we could really afford to cancel a class because it would have screwed up our synchronization. And I certainly didn't want to do lab without having class today. It was very critical.
I was fine with it. I actually was almost on my way though, so.
I was very worried about that, and I was trying to get an email out, and I was also trying to make a decision. And it's always difficult when you kind of, you know, that I was in a very difficult decision where I had to decide what would be the best. And I figured since we've already been doing this for so long, one more couldn't hurt us, and it would at least save us a drive in the snow and all the rest of it. I didn't want to start class at noon. The whole thing was just a very tricky thing. Ethan Brown.
Yeah, I'm looking. Wait, can you go over what exactly we're trying to solve for now?
Well, we're solving for the period of the I.S.S. is the big goal, but we have to do some stuff first. We have our A, our semi-major axis of orbit, in kilometers, but A needs to be meters. So I need to do a unit conversion. So our first goal here is convert A to meters. And it's currently 6,800 kilometers. I wanted you to use dimensional analysis to do that. Do you know your steps of dimensional analysis?
Not off the top of my head.
Do you have them in your notes?
I'm so unorganized. It's terrible.
Well, might want to look into that. But meanwhile, we gotta see. One of the things I'm trying to do is I know you guys are going to pull bullshit like this and not actually write down notes, and I know you're going to be terrible. I already
You gotta write.
So I need to force you guys. I have two options: let you be terrible or force you to learn the 4 steps of dimensional analysis. My idea is to force you to learn the 4 steps of dimensional analysis. Now, I don't want to, can you guys see me holding up to the computer screen, my phone here? Are you guys seeing this? All right.
Yes.
So I'm going to go to my lectures and we're going to find the 4 steps of dimensional analysis because it's so fucking easy, Ethan, you wouldn't even believe it. You just go to our second lecture, lecture 1 part. Oh, I had to kind of post a funny thing, didn't I? We actually did lecture 01, but I went to a previous lecture for this. Whatever, I'll just grab my AS1010 lecture because it's quite easy. Lecture 01, 1020, lecture 1, part 2. Okay.
But I mean, I got the steps right here. I always have them in my folder if you want to.
I know that, Lionel, but see, he can't go and look up the steps in your notebook. But I'm trying to do 2 things at once here. I'm trying to show him that he could just go back and get the notes the way he was supposed to. And they're in the announcements section, but I kind of want to do this quick because we're using up airtime here, right? So what I'm trying to do is figure out where are my goddamn steps of dimensional analysis. All right, I might actually have to use yours. Damn it. Okay. I said they were easy, and they are easy if we went to our announcements section. All right, let me try to do this a different way. You go to announcements, Ethan, okay? You go to the lecture that I posted, our second lecture. So this is lecture 01, and we're going to go to lecture 1, part 2. You need to write this down, and I'm not just talking to Ethan. I'm talking to all you people who didn't do it right, okay? You need to get down the 4 steps of dimensional analysis before that exam comes up, or you're going to be miserable sons of bitches. And oh, there they are. Look, I'm even going to give you the bloody timestamp. The timestamp is 43 minutes and 13 seconds, okay? And it's somewhere around there. Copy. I'm putting it right into the damn chat log. Ethan, your job for today is to get that into your notes. And now, Ethan, because I'm trying to demonstrate, there we see, get out of my way here. Let's see if we can write these down here. All right, so what's that first step? What does it say? Can you see my screen? Just look at my screen.
All right, I'm looking at your screen.
What's the first step? Just read the words.
Write down the numbers to convert with units.
And look, shoot. Where was I here? Sorry. Oh, give me a break here. Okay, here we go. So I already wrote it down. 6,400 kilometers. What's the second step?
Multiply by a division bar.
All right, so that's what we're going to do. What's the third step?
Put units in first to cancel.
So you got to give me some units. Top and bottom. Do you know what I mean by that?
Oh, it's lagging so much for me. Yeah. So we're trying to get kilometers into meters. So put kilometers over meters.
Does that cancel out kilometers? This is kilometers on top. Kilometers times kilometers over meters gives you kilometers squared per meter. I don't think
I know the opposite. Meters over kilometers.
That's right. That's why we have to do that step first, okay? We want kilometers on the bottom, meters on top. That will cancel out our kilometers. Okay, the last step, let's see if we can see it there. At timestamp 42 minutes and 30 seconds. Okay, we'll screen that. What's that say?
Put numbers in second using conversion factors.
In other words, you need a conversion factor from meters to kilometers. Do you have such a thing?
No, I don't.
Well, I've got news for you, Ethan, and I'm kind of picking on you for a reason because there are other people who are in your shoes. You need to take these notes. They're so important because that's where I tell you all kinds of useful things like 1 kilometer, write this down now, equals 1,000 meters. You can't just watch the labs and the homeworks. I don't know what has been going on, or if you writing stuff down helps you know where to find it. Okay, so your job is to put these numbers in here somewhere. It's okay, you have to stumble through this. So give me a number at top and bottom. Just take a guess.
It'll be like a lot of meters. So right, it'll be like
No, I want to know a number here and a number there. That's all I want. This is
so 1 kilometer equals 1,000 meters. It'll be
Yeah, and where do I
Gotta be
put
a-
the 1 and where do I put the 1,000? I want you to be very specific about that.
Oh.
In other words, does the 1,000 go on the top or the bottom? That's what I'm trying to figure out.
On the top.
Because that's where the meters are.
Yeah.
And then I put the 1 on the bottom. Okay. Let's see if we can do this in our head. How many zeros?
4. No,
No.
3, man. 3.
And then here you've got 2 more zeros plus the 8. So if I put this in scientific notation, it would be 6.8 times 10 to the what?
Just ask me a question. I couldn't even hear that.
Yeah.
10 to the
This one's
6.
6 meters. Okay. Okay, we've converted our A to meters. That part's done. Ethan, I'll stop picking on you for a bit. But Ethan, if you don't have, you know what I would do? If I were you, I would have.
No, I think I have them. I had them written down. I didn't have them accessible. Like I don't know where exactly in my notes they were. Like I definitely remember writing down what this equaled that and that equaled that through one of the lectures one day. They're in my notes somewhere. It would just take me a little bit to find them because I'm not organized well.
That's fine. And I've suffered from that as well, Ethan, but I learned by going to classes like this and having this experience. I mean, I still struggle with it, to be honest with you, but I'm trying to reach towards the light, and I want you guys to reach towards the light as well. Let's have those notebooks. Let's have all those notes there. And it does take a few minutes to fish it out, but basically I'm trying to pretend like we're in the exam and like, what would we do if we had to do this by ourselves? It's always a little bit more difficult than when I do it because I know what I'm doing so well, you know? Anyways, okay, I don't want to get too meta here. Let's focus, Ethan, I'll let you go, leave you alone for a minute. I'll mute you. Let's focus for a bit on the total mass of the system. M total is the mass of Earth plus the mass of the I.S.S, which is 6 times 10 to the 24 kilograms plus, let's see, 400,000 kilograms. Why don't we try adding those two numbers together using our calculators? Everyone punch them in. If you punch them in, you get 6 exp times 10 to the 24, which is just the mass of the Earth. What happened there?
Six times 10 to the 24 is so many times greater than 400,000 that it makes 400,000 insignificant.
Yeah, and so this is a trick. The total mass of the system is such that we can neglect the mass of the I.S.S. You cannot always do that, but this is a trick that you can do sometimes. You kind of have to know when to neglect. And that means this total mass is really just going to be the mass of Earth. So M total is approximately just the mass of Earth. We're now going to rewrite this equation, but we're going to take the square, we're going to flip it to the other side. If you put the square on the other side, it becomes a square root. So P is going to be equal to the nice big neat square root. Okay, here I need to sort of put this down. Let me adjust my camera angle here. The nice big neat square root of 4 times pi squared times, now we have to put in our A, which Ethan Brown, which Ethan Brown helped us get is 6 times 10 to the 6, 6.8 times 10 to the 6 meters. So I'll do open parentheses, 6.8 times 10 to the 6 meters. That's got to be cubed. So we'll put that in parentheses. Divided by big G, 7 times 10 to the minus 11 meters cubed per kilogram per second squared times just the mass of Earth. 6 times 10 to the 24 kilograms. And evaluating this is going to be a little bit tricky the first time around. Does everyone have that written down? Okay. Here are the tricks that we're going to have to pay attention to. We've got to remember to square the pi. We've got to remember to cube A. But the most important trick is right here. When we get to this on our calculator, even though it says times, we're actually going to hit divide. And that's because the calculator needs to know, that's not a plus, by the way, that's a times. I just wrote it crooked. The calculator needs to know that we have to divide there. So watch me do this and punch along with me, okay? We're going to do 4 times pi squared times 6.8 exp6. Then I'm going to cube it. The cube is right there. So I have to go shift x cubed. Now I'm going to divide by g, negative 11. And I will divide by the mass of Earth, 6 exp24. Then I will hit equals. Now we've got to square root this. So at the end, we're going to hit shift square root. Everyone hold up your calculators and show me that that's what you got. Good, good. Ethan, what's up with you? Ethan Brown.
You went way too fast for me, and my screen is lagging way too much for me to catch all that.
All right, so let's do it
I
again.
understand what you did.
So can we try it again slower, Ethan?
Yes, yes. If
Okay,
you would like to.
Each time you're going to tell me, keep yourself unmuted here. Tell me when you're ready to proceed so that we can do it together.
I'm ready right now.
4 times
Yep.
pi
I couldn't even hear what you just said there. God damn it.
I said you have to hit pi by hitting XP.
Yeah. Okay. 4 times pi. Got it.
Squared
Squared
times
times
6.8
6.8
exp6
exp6
shift cube
shift cubed
divide by 7 exp negative
7
11.
exp negative what?
11.
Yep.
Now divide by 6 exp 24.
Got it.
Equals we're not done. Shift square root.
Got it.
Show me. All right, what should we round this to? 2 sig figs. What do I round to, class?
5,400
Units?
seconds.
Good.
Okay.
That's our answer. But what we should do, because 5,400 seconds is, it's not obvious what that means. Let's convert it to minutes. Division bar, what units go top and bottom? Any day, people.
Minutes on
Minutes
top,
at the-
seconds on bottom.
Okay. What's the conversion factor?
That's 1 minute is 60 seconds.
Okay, so we divide by 60. 90 minutes. Which is an hour and a half. And this is our lab. Everyone let me steady my camera here. Take a good long look at this because this is what I want turned in. You guys got that? All right.
Really, the amount of light that is not in my room is really affecting how much my calculator works.
Well, that's something I'd like to say as a general comment to the class. Part of doing work at home is having a really good space set up. And it might not be obvious to you, but I've got a little desk here with a lamp, and I kind of have like some nice pencils and tools. Ethan, oh shit. Guys, hold on a second. Hold on. Is that falling over? It's collapsing. Okay, the whole fucking thing is collapsing. It's coming unstable. All right, we gotta deal with that. Okay, sorry guys. My entire wardrobe just started collapsing and my girlfriend almost got crushed. I'm sorry. That was weird. That's never happened during a Zoom before. I need to deal with this emergency. You guys have your thing. Now listen, I was debating whether we should do it, and keep an eye on that, Jordan. I need to go, but I was debating on whether we should turn this in person or on Blackboard. Since we did it on Zoom, do you want to just take a picture and we'll upload it to Blackboard? I changed my mind, okay? Just put it on Blackboard the way you've done, and going forward, we'll do it in person. Sound like
Just for today, I agree with that because I put this in my notebook accidentally.
that thought actually, Ethan, crossed my mind. I was going to tell you some stuff about the period of the I.S.S., but right now I have to make sure that my whole wardrobe doesn't collapse, smash into a million glass pieces and kill my girlfriend. Okay, so.
I feel like that second part's more important.
Yeah, yes, okay. I know. Listen, I'm teaching my night class in person tonight, but I'll be teaching you guys in person on Wednesday, okay? I'll have this posted by 4 or 5 o'clock.
All right. Even though I'm in the night class, can I come on Wednesday?
You want to come to the day one?
Yeah, at least like for this week, because I showed up today. I might as well like finish it. And if I showed up tonight, like, would I have to show up like halfway through? Because I've already got half the lesson
And
done.
we'd be doing the lab at the end, so that would be kind of awkward. Yeah, Mia, if you're in the night class, you can totally just come to Wednesday's day class and do the day homework. The funny thing about that, Mia, is next week, we're not going to do the homework for the night class this week. We're going to do it next week. So you would skip office hours and just come at 6 p.m. next week, okay?
All right, got it.
Because, well, hold on. If you come to Wednesday's lecture, will you stay to do the homework afterwards?
Oh yeah, yeah.
That works for me. So that's cool, because then you'll just rejoin the night class at 6 p.m. next week, okay?
Got it.
Cool. I'll see you guys later. Bye.
Have a good day.